Tonight on Nova, it was a stunning announcement from two respected scientists.
We've established a sustained nuclear fusion reaction.
The claim was staggering, but the details were sketchy. At labs around the world, the chase for fame and fortune was on.
We've sat for 5 years on this, and I think the people who are doing the work should respect that.
Had they discovered cold fusion, or was this just a case of confusion in a jar?
Funding for NOVA is provided by Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. And the Johnson & Johnson family of companies, supplying healthcare products worldwide. Major funding for NOVA is provided by the financial support of viewers like you.
Inside a lump of metal, inside a test tube filled with water, began one of the strangest stories in modern science. At first, it was just another unlikely experiment, but it quickly grew to encompass far more than the elements in the test tube. It was a science story that became a news story, a big news story, and it took the world by surprise.
This is the CBS Evening News.
The first remarkable thing about the story is that almost everybody who heard about it, scientists, reporters, and the public, heard about it on the same day.
Come in large, expensive packages. Instead of experimenting with giant machines costing millions of dollars, a British and Utah scientist may have found the answer to our energy problems in a glass tube, sitting in a bowl of water in a
More
basement
people saw
laboratory.
these pictures than watched the moon landing 20 years ago. On Thursday, March 23, 1989, the University of Utah held a press conference for the scientists to explain their amazing discovery.
This experiment has to be approached with some caution, because this device, if this device worked as rapidly as the small-scale electrodes which we've run, this would be generating about 800 watts.
One was Martin Fleischmann, professor of chemistry at the University of Southampton and fellow of the Royal Society of London. He's renowned for his imaginative and brilliant work in electrochemistry.
We've established a sustained nuclear fusion reaction by means which are considerably simpler than conventional techniques.
The other was Stanley Pons, Dean of Chemistry at the University of Utah, a one-time student of Fleischmann, and a man with a reputation for high-quality experimental work.
To such an extent that these deuterons...
Pons and Fleischmann announced their discovery to the press before they told even their closest colleagues. Their decision to do so has haunted them ever since. But the word was out. Two respectable scientists said that inside an ordinary test tube they could create nuclear fusion. By now, everybody has heard of fusion. It's the nuclear process that powers the sun. It's the power of the hydrogen bomb. It's also a way of extracting energy from ordinary water.
The promise of virtually unlimited radiation-free energy is something that is worth spending perhaps billions of dollars on.
It is, in my opinion, the real solution to energy in the future. I mean, the sun is the fusion reactor. If you look at the universe right now, the sun is a fusion reactor. It's hydrogen slowly turning into helium. The stars, these are all fusion reactors. This universe, nature, has chosen fusion as its power source. And I think that's, it's kind of philosophical, but nature is usually right about these kind of things.
Global warming, ozone layer, the greenhouse effect. They'd been on everybody's mind. They were on television every night. The Exxon Valdez oil spill story had actually broken on the same day as the press conference. Most of the time when we think about such disasters, we're reduced to despair. But perhaps this time, from the deserts of Utah, somebody was offering a real answer. Soon we might all have safe, small fusion reactors. No more greenhouse effect, no more fossil fuels, no more global warming. The possibilities were tremendous if Pons and Fleischmann were right.
I subscribe to the views of Karl Popper, Sir Karl Popper. He says you can never prove anything right, you can only prove it wrong. And I think we have to go now through a phase where everybody will try. We have tried very hard to prove ourselves wrong, all the way down the line. We have to now wait and see, are we right? What's the scope of this? And only the future will show where it fits in.
Karl Popper's method of checking a theory began that evening on the news, at a time when labs were quiet and scientists outside Utah were enjoying a drink.
Martin Fleischmann and Stanley Pons found a way to simply fuse deuterium inside electrodes.
The news astonished everyone.
Stan and I thought this experiment was so stupid that we financed it ourselves.
The scientists were attempting for the first time to...
At MIT, the experiment caught the attention of a group of undergraduates, members of a physics group called the Pikas.
We got pretty excited about it. We talked about it for a long time, finally decided, let's do it. It was around 11:30 at night. We ran around the corridors looking for the materials we needed. It was sort of a scavenger hunt.
It was the excitement of being at the forefront of what might become a new technology, of saying I was there when it first happened, of trying to verify the claims of another scientist when those claims seemed, outrageous.
We probably didn't really believe it was going to work. I guess we knew that our attempt at it was sort of a slipshod attempt. We knew that wasn't going to work, but I think we did really want to believe.
It wasn't difficult at all because it's a very simple experiment that any chemistry student would learn in their first year. So it's just finding a jar, a battery, and this palladium, and that's all really you need to do.
It's a breakthrough in an area that we've been spending a lot of money and putting a lot of effort into. It's a clever, cheap version of something that people have been piling, lots and lots of effort into. Instead of, it's the sort of thing where, the entire nation is working at getting fusion to work, and they have these huge generators, and they have, the one at MIT has a whole row of municipal power generators devoted to it. They have their own special cable going over to Cambridge Electric Light Company. They get blamed if there are glitches in the power line from other people because everybody assumes that it's them. This is high power, big science. And then here come along these two electrochemists and say, oh, yeah, we'll just do this, poof, fusion in a jar. That's really, that appeals.
Previous attempts to sustain a fusion reaction had indeed involved big science and big money. Over the course of 35 years, billions of dollars have been spent to produce deadly pulses of super high electric current that smash atomic particles together in attempts to make them fuse. Still, even the most optimistic predictions talk of decades before there is a working hot fusion reactor. Hot or cold, fusion uses the same source of fuel, a naturally occurring isotope of hydrogen called a deuteron. The nucleus of the deuteron is made up of one neutron, the dark particle here, and one proton, the light particle. Whenever two deuterons collide and fuse, the particles rearrange themselves, form a new atom, and eject a nuclear particle with tremendous energy, measured in millions of electron volts. The rearrangement can take one of several forms, producing either helium-3 plus a neutron, or tritium plus a proton, or helium-4 plus a gamma ray. When any form of fusion occurs, both energy and nuclear products are produced and can be measured. Normally, deuterons will fuse only very rarely. You'd expect only one fusion a day in the whole of the galaxy. But on the Sun, the heat and pressure are so intense that the particles are driven together until fusion is happening all the time and energy flows out of the system. Previous attempts to create fusion on Earth concentrated on trying to reproduce the conditions of the Sun. For hot fusion to take place, extremely high pressure and extremely high heat, over 670 million degrees Fahrenheit, have to be achieved and maintained for long enough to get the reaction going. Pons and Fleischmann offered hope that all that dangerous and expensive heat and pressure were unnecessary. In their experiment, they used the rare metal palladium, which has a very strange property. Because of its structure, it can absorb deuterons the way a sponge soaks up water. A cube of palladium can actually bulge with deuterons. Fleischmann and Pons claimed that they could make fusion take place at room temperature by simply packing the deuterons inside a rod of palladium using an electric current. The bubbling was not unusual, but after a while, they claimed they found something that was. Heat was being produced, which meant that the tube had become a source of energy. They also said that they had detected some of the signature nuclear products which proved that fusion was taking place. After the startling press conference, the world's astounded scientific community began a series of relentless attempts to duplicate the Utah experiment, to prove or disprove Pons and Fleischmann's remarkable claim. That Thursday night, the MIT undergraduates didn't find anything. They hadn't seriously expected to, but they had started MIT's cold fusion research effort. A photograph of their evening's work found its way to senior plasma fusion scientist Marcel Gaudreau.
Late, I guess, that Friday, we were kind of like, it's at the end of the day, Friday night, and it's the Easter weekend, so everybody's kind of leaving, and there's a little bit of chatting in the hallway. And lo and behold, one of the guys right there came up with this little piece of paper here, and it basically described an experiment the Pica people had done in one of the labs, and I was just like amazed. I thought it was a very good, very quick experiment. Now, for something that was done the night of the press conference, is very good. It had all the basic ingredients, palladium, and the heavy water, and so on. And it described how they measured the temperature, and they had a little picture. It's kind of like a page in a notebook, and I think this will be something in our archives for a long time. I think it's really what got me really going. I saw this and said, hey, these guys are really rolling, and we ought to really try to figure this thing out. We'd spent years and years working on control fusion, and then suddenly you have this little jar like this, and we ought to figure out how this works.
I thought this experiment was so stupid that we financed it ourselves.
It was highly unorthodox that Pons and Fleischmann had not published a detailed paper of their experiment, but they hadn't, and it was impossible to contact them. So some of the world's most eminent fusion scientists ended up getting their data off a TV screen.
To the right of the experiment, and then you can see the 3 tubes. These are just regular tubes charging, and the good thing about it, about this picture, is you can actually see the wires clearly in series. Wow, it's hard to see a little bit, but if you take some time, you look in there, you can see this wire goes around like this.
He's got like 4 cells there, and 3 here and 1 in the water bath.
And the thing that we don't understand is this tank.
It's not hooked up to anything. Where is it?
And how long does the charging go on? I mean, if they look at energy balance, if you get
they wore out a videotape trying to work out the wiring of the batteries.
Right. I mean, you have to know how much energy you've put in, integrated energy you've put into the cells.
In fact, the batteries were irrelevant. They were just there to power a detector, but the MIT scientists had no way of knowing that. A little more information came from the print media. Martin Fleischmann had spoken to a journalist on the Financial Times of London. The father of one of the MIT team, Martin Schlau, arrived from London 2 days after the press conference.
He had the Financial Times, and he made me aware of an article and said, what do you think about this? My dad is not a scientist, and we always have a little exchange. And I looked at it and said, that sounds so easy. I think I'm going to try that.
A printed diagram, even from an unusual source, made it seem more likely that the MIT team could reproduce the experiment. During the weekend, the group worked around the clock, looking for heat and fusion products. At first, the team half expected to see something glowing, but nothing happened.
Hey, it stopped. From the news reports, we got, sketchy details, and one of them was that you have to have a rather thick palladium rod. So the first thing we did on Monday when the shops were open is try and dial around and find a palladium rod, which proved to be not such an easy thing to do. We got the last palladium rod in New England. We had to drive up there and get it ourselves. And that evening, all of us were working in a team together. But we were so excited that we stayed up all night.
One of the strongest indicators of how much radiation to expect was the fact that Pons and Fleischmann were still alive. That put a maximum on the quantity of fusion products. It was still sensible to take precautions, though. Ironically, the safe area was under the nuclear reactor. The team kept watch on the experiment by a TV monitor. They worked for days, but still no glow and no explosion.
We really were realizing there were just too many degrees of freedom. Even you would think that once you knew what it looked like, that, well, how complicated can it be? Well, if you just look at what power you needed, you didn't know the voltage, you didn't know the current, you didn't know if it was pulsed. Even if you knew it was pulsed, you didn't know it was pulsed quickly, how often it was pulsed, and so on. The solution, well, had an infinite number of variables, because even if it was just one chemical or another, you know, there's thousands of chemicals, maybe it was a combination of chemicals. So there's just, literally, we're realizing that we needed more information.
At the British Nuclear Research Establishment at Harwell, there was a research group that did have more information. A couple of weeks before the press conference, Fleischmann had actually given them details of the experiment.
97 and 376.
Pons and Fleischmann claimed to have measured the heat that was essential if their experiment was indeed a source of energy, but to claim fusion, they also had to detect certain nuclear byproducts, neutrons or tritium or gamma rays. The British work at Harwell covered both heat and fusion products, but their search for neutrons was particularly thorough. They placed bubbling cells in the center of concentric rings of neutron detectors. They also took steps to make sure that no other effect would interfere with the result. Electrochemist David Williams.
Well, what you have to do is compare a powered cell with an unpowered cell, so that you can get rid of the effects of variations in the background and funny effects due to the counter and all that kind of thing. You have to exchange them every 5 minutes, and you have to do it for hours and hours and hours, and it is unbelievably boring. Now, we did it like this for the first couple of runs because there was a panic about repetition of the results from Brigham Young University. But obviously we then automated this process, and it just shunted backwards and forwards there, in and out, every 5 minutes for weeks.
Okay, that's it. 385, 392.
You don't do science unless you have a sense of vocation.
405 and 366.
When you get gripped by something like this, you work all night. I mean, people do it. And the telephone was just going like crazy. The reporters ringing up every 2 minutes. One reporter from a popular newspaper, he wanted me to tell him that everybody was going to have a little immersion heater in the corner of their room, and this was going to solve the energy problems. Well, I wasn't going to say that. I think people were gripped by a great sense of excitement. And one of the things that you notice with things like the cold fusion and the high temperature superconductors is all of a sudden there seem to be huge numbers of scientists who have free time, who are able to do things like this. And I reckon that what it is that all of the time here they are, they're meeting their milestones and their targets and all this kind of stuff. And all of a sudden something like this happens and they're released. And it's like away they go on this fantastic chase.
After a few weeks of the chase with still no result, Williams tried to call Fleischmann, who was, after all, a colleague and friend of his, to ask what he thought might be going wrong.
After this press conference, things, I don't know, I think things are probably difficult for Martin, and the amount of communication that we could have was less. And Martin said, and I think rightly, that he wanted any confirmations to be independent confirmations. So we didn't have a lot of contact. I did let them know that we were getting negative results, but we didn't really have a proper opportunity to discuss exactly what we'd done and why it should be negative. I think that kind of thing takes a lot of time to explore and get right. And I think Martin, after this thing exploded, Martin simply didn't have any time.
Discussion with Fleischmann wouldn't have been so crucial if a full paper had already been published. The international scientific community has its own way of doing things. Even the most earth-shattering discovery must be reported in a professional journal such as Nature before it is released publicly.
We like to think that we publish the most important scientific discoveries that people make, from the discovery of radioactivity at the turn of the century to the discovery of the positron, the neutron, the splitting of the atom in the early 30s, the discovery of nuclear fusion in 1939, DNA in 1953, continental drift between then and 1962 when it was tied up. And we have a very, very good record in that field. And so I think people, our readers, look to us to provide authentic reports, in the words of the authors of research, of important discoveries.
Every article submitted to Nature goes through a rigorous checking process called peer review. The draft is sent for assessment to various experts in the field. Pons and Fleischmann had submitted an article the day after the press conference. The experts came back in record time with requests for more detail.
We sent them these comments. As I remember, the paper went through two series of revisions. The first produced a paper that was still unsatisfactory to the referees, and we asked them a second set of questions, telling them, look, we don't care how long the paper is. We want these questions fully dealt with. And they decided, I think it was quite legitimate from their point of view, that they didn't have the time to do that. They had so many other things to do.
In early April, Pons and Fleischmann did publish a paper in a less well-known journal, the Journal of Electroanalytical Chemistry. It was faxed around the world. Faxes of faxes were passed on to everybody who was interested until people were receiving illegible copies. But the paper satisfied almost no one. It answered none of the questions that would-be fusioneers needed to know. But information, or at least opinion, burst out in the form of electronic mail. Many of the world's scientific laboratories are connected by computer links. They carry important information and also gossip, rumor, and speculation.
Physics grad students here at the University of Washington have detected signs of tritium, possibly produced by
technology. But I'm a CS major at a small university, and we don't talk.
One of the most interesting things about the CNN broadcast last night was that the man explaining the experiment to the reporters was touching the glass bulb containing the active elements. None of his bodily parts fell off. By the way, all you fusion skeptics, could you shut up for a while? I think it's pretty clear that there is cold fusion going on.
They have as much right to be skeptical and to talk about it as you have to believe.
You're right, you can have a big laugh at the rest of us in a month or two.
By mid-April, independent confirmation of Pons and Fleischmann's results were being announced, again on the evening news.
New promise, puzzle, and mystery tonight over what may be a momentous advance in fusion nuclear energy research.
Researchers in Georgia and Texas said today they've duplicated parts of the Utah experiment that created such a tempest in a test tube. The claim that nuclear fusion can be achieved at room temperature. And researchers at Texas A&M University say their experiment, like Utah's, produced excess energy. Georgia Tech scientists say their experiment produced high levels of neutrons, confirming nuclear fusion is taking place.
It's so fantastic that simply to confirm it is a major thing. There was a literal explosion of interest. There were so many cameras all of a sudden. I thought, surely there must be a plane wreck on campus somewhere, but as it turns out, they came to photograph us, this very room here.
The Italians, French, and Swiss announced they're trying to duplicate it. Scientists in Moscow, as usual, claimed they'd already done it 20 times at least. Georgia Tech is rechecking its numbers, but researchers in Texas and the University of Washington say they've been partially successful. No matter, since the word broke, the price of palladium, the metal used in the experiment, has soared $30 an ounce. And the University of Utah, where it all began, has a growing list of Fortune 500 companies wanting a piece of the action.
By the 27th of April, 24 labs were known to have reported some sort of confirmation. Nobody knows how many had actually tried the experiment. As fusion fever increased, the University of Utah started to work on raising funds for further research and development. They employed a firm of consultants to try to persuade Congress to support special emergency funding.
American scientists at Raytheon invented the microwave oven, but today it's Korean and Japanese companies who produce 90% of the world's microwave ovens. American scientists at RCA invented the color television, but today European and East Asian companies produce over 97% of the world's color televisions. American scientists at Ampex invented the VCR, but today Japanese, Korean, and European companies produce over 99% of world VCRs. American scientists funded by DARPA invented the computer numerically controlled machine tool, but today European and Japanese companies produce over 75% of the world's...
The university wanted $25 million from the federal government to build a national center for cold fusion research in Salt Lake City, to put America and Utah in the forefront of this promising new field.
Are you aware of any attempts by the Europeans or the Japanese scientists to develop viable cold fusion?
this is being researched around the world, and I've had confirmation of our results from far afield, very far afield. You can guess where that might be.
There is an alternative, and that's what I'd like to talk to you about today in the remaining few minutes. It's an alternative that says that America is prepared to fight to win this time.
Back in Utah, fusion fever took on a kind of party atmosphere. A definitive collection of T-shirts will one day be a valuable artifact in the annals of scientific history. But there were problems on the horizon. Of the two signs of fusion, heat and nuclear products, some groups saw one and some saw the other. Very few labs reported they'd seen both. This was partly because it was very difficult to detect the two at the same time, but also because they required sensitive measurements that were subject to error. There were even rumors that in Utah, a physicist had tried to measure neutrons in Pons and Fleischmann's own lab, but had found nothing. The fusioneers started to become a little defensive. Even the groups that claimed positive results reported they were not reproducible. Sometimes it worked, sometimes it didn't. Nobody could explain this, and it began to make cold fusion a slightly less scientifically respectable phenomenon.
Without these exact facts, we will never be certain that our samples have reproduced their samples.
I beg your pardon, the background is available in the corrections to the paper.
That might be. I would like to specifically hear whether or not helium...
Could we go on to the questions, please?
This experiment hasn't been reproduced by any national laboratory or any university yet without a good football team.
Mudslinging on television is not going to get any of us anywhere.
Zero-energy thermonuclear assembly, or ZETA, is used by British scientists at Travle in a tremendous project. The harnessing of the power of the H-bomb for peaceful...
Some scientists recalled a British experiment of the 1950s to which the media had also given sensational treatment. At first, experimenters believed they had created thermonuclear fusion.
Hydrogen from water, so one day we may get unlimited power from the sea.
The press and public went wild, but within 3 weeks of the news story, embarrassed scientists and journalists had to admit that they'd made a mistake. The Holy Grail was still missing. Neutron counters like this old BF3 are still being used today. Modern versions have been made much smaller so they can be moved. Quite how they are moved turned out to be a crucial factor in the career of Georgia Tech's Jim Mahaffey.
But we were talking, as it turned out, one evening with some guys at Lawrence Livermore out in California. They had exactly the setup we had, using the same type of detectors, same water bath and whatnot. And they were doing the same interim control that we did, which is you take the detector out of the moderating solution and put it behind the boron blocks, thus shielding the detector from any neutrons made in the experiment. We had done that. We found that when you put the detector behind the neutron shield, neutrons fell off to background, which seemed to confirm that whatever was going on in the cell was making neutrons. They did the same thing, only whereas I picked it up by the cable daintily like this, one of the guys held it in his fist. And as he held it in his fist, he noticed the neutron count going up. He thought, that's odd. So they got a heat gun and played it over the tube. They found the neutron rate would go up just like it would in the experiment. And we were on the phone with them. They said, you better check your BF3 tube. So we took it out and put it in a glass of simple hot water. And in fact, it went up times 600 over background. At that point, we said, gentlemen, we are dead.
So there was another press conference.
It's not nearly as dramatic and conclusive as what we thought we had. The press reaction to that was maybe 7 times greater than the initial press reaction. Whereas at the first conference, I think there were 7 cameras. At the second conference, there were 30 cameras, all trained on me. Had to explain what had gone wrong, It was a very interesting time to be alive. I remember having heard about a conversation where someone said Georgia Tech was actually paid off by the oil companies to suppress the data. Well, the oil companies never approached me on that. I'm still available, ready to suppress just about anything if the price is right. But they never even tried.
Despite the setback at Georgia Tech, researchers have kept their sense of humor.
Let me just tell you that we've renamed the experiment the Shroud of Turin.
In Britain, Harwell Laboratories reported similar experiences with the neutron counters. In one case, a faulty plug registered a massive surge. In Spain, a group found that they could increase the count simply by opening the window.
Measuring neutrons was interesting to me. I'd never known anything about it before. I mean, I guess as most chemists might think, that you just go and get a neutron counter out of the stores and you point it at whatever the source is supposed to be, and you look at the counts, they're registered. And it's not like that at all. I mean, it was pretty impressive to me, the rigor with which the experimental physicists went about this particular job. There turned out to be lots of reasons why you get signals on neutron counters which have nothing whatsoever to do with the presence of neutrons.
Detecting neutrons wasn't the only problem for the British group. Measuring heat within the cell, calorimetry as it's called, proved incredibly difficult. There were too many variables and not enough controls.
Pain as well. You have heat loss from the top here out into the air, and that is unquantified. So, and it is an error. So here we have this thing which the accuracy of your statements, if you like, depends upon the accuracy with which you can make measurements with this very simple instrument. But it's not a simple instrument, it's a complicated and subtle instrument. Now, when we started this off, we were pretty naive. This was a design of Martin Fleischmann's, and we thought, it would be pretty straightforward to reproduce his results with this. Now, we were lucky in which we had an expert calorimeter man who was working with us, who was able to show us the problems. And we also did a lot of blank experiments, which also brought these problems out very clearly, and showed that the original claims, anyway, were well within the bounds of experimental error. And we checked our results by using different calorimeter designs. We had 3 different calorimeter designs. The reason for that was that we wanted to be sure that there was no effect that in our results from some unappreciated aspect, a subtle aspect of the design of the instrument. And so we used different instruments with different principles behind them. And by doing that, we were able to be pretty confident, actually, that we had found nothing.
In Boston, MIT physicists also reported that they found neither heat nor fusion products. Tempers flared.
We worked for 5 years on this, and if people think that they can go and have a quick dabble and find the result, then fine, let them do that. But that's not our style. Our style is to do definitive experiments over a long period of time. And we disapprove of the way in which
experiments
are being done at the moment.
Papers written at lunch and published negatively that evening. It doesn't happen.
We've sat for 5 years on this, and I think the people who are doing the work should respect that.
One of the most serious blows to cold fusion came when an MIT physicist closely analyzed some of Pons and Fleischmann's own data.
In a paper released today, the MIT scientists concluded that a major part of the Utah claim is wrong.
I mean, that's speculation.
Richard Petrasso, an expert in gamma rays at MIT, examined one piece of information, which had been on television as well as in Pons and Fleischmann's published paper. The trace on the screen was meant to be evidence for gamma rays, a fusion product. But Petrasso thought that there were 3 things about it that looked wrong. First, the peak was far too narrow. And second, the trace had the wrong profile for a true fusion gamma ray.
Those 2 fundamental points negate the possibility that they really observed this characteristic fusion gamma ray. There's also a third feature, and that is that the peak is much too large compared to the background radiation. We know, because their lab is on Earth, that there's these characteristic gamma rays that come up from the ground. In this case, it comes from uranium-238. It's around here, and no matter where you go, England, Europe, America, uranium is in the ground. And this causes background radiation. And this background level should have been far more elevated with respect to their signal size than they show. So we knew from that consideration alone that the energy had to be wrong.
The dubious gamma ray data only added to the mounting skepticism of researchers who were having trouble detecting fusion products. Federal research funds never materialized. Despite all the doubts, Utah authorities pressed forward with ambitious plans. In April 1989, the Utah State Legislature voted a $5 million grant to start up a National Cold Fusion Research Institute. The University of Utah also announced that it had received a $500,000 anonymous gift to support work at the new institute. Before all this began, the University of Utah wasn't known for work in nuclear fusion. The university believes that its critics, both scientists and the press, have been too quick to judge them harshly.
We're not the usual stopping place for any of the national press in terms of regularly reporting on science work from the university other than genetics or artificial organs. The big research centers that deal with this area are on the East Coast or the West Coast. So there's also the isolation involved, and there are some here who've thought that had we been a Berkeley or a Stanford or a Caltech or an MIT, that the announcement might have been viewed a little differently.
A disturbing pattern emerged in cold fusion experiments. Labs at high-prestige universities generally got negative results. Elsewhere, results were often positive.
I was absolutely astonished that when I took Northern Europe, Northwestern Europe, all the results were no, 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 no. They couldn't find it. And when I took Southern Europe, it was all yes, yes, yes. When I took Eastern Europe, it was all yes, yes, yes. The United States divided into two groups. If you took the major laboratories and what I call the greater region of the New York Times, where it was read very much, it was all no, no, no. If you took the remainder of the United States, the southern part, it was all yes, yes, yes. If you took the rest of the world, it was all yes, yes, yes. And this rather horrified me.
Wherever they were made, confirmations of cold fusion were announced much sooner than negative results. Morrison has a theory about why that is.
I think the reason is when a very interesting, exciting discovery is announced, there are many people start working. And if, for example, you have 100 people start working on it, perhaps 50% do careful experiments, find nothing. Another 50 do experiments and, they're not quite sure. But 10 of them, just by this sort of fluctuations, they find positive results, and results come out. And since they find a positive result and it's already been published, then it's a confirmation, and they don't have to be critical because just confirming something. So they announce no problem, they hold press conferences. Great. Whereas the 50 who found nothing and who do a good experiment, they're worried because to say a colleague is wrong is very dangerous. Because maybe you're wrong, so they worry and they're reluctant to publish. It takes time, they check and they say, well, maybe there's some secret we have to check on. So they're slow. So in the initial period, you only get the confirmation of that. Then gradually one or two have the courage to publish, and then suddenly a lot more publish. Then suddenly everyone realizes that it can't be right. And this avalanche of results that have been waiting comes down.
When negative results were first reported in the news, scientists working on cold fusion were astonished by the angry response from the public.
All we wanted to do is just one good experiment, clean experiment, where we thought we know how to handle the background. And the reaction we got from the public was that, you scientists you're the only obstacle in the way of development of science. It's because of you that the dream of cold fusion, cheap energy will not come true. Like, if we get rid of you scientists, we will have good society. That, in fact, you are now stopping us from getting it. I was very disappointed from getting these letters. I was inundated by letters, telephone calls, people accusing me, and all I wanted to do is just one experiment which I thought I can do, which would just look into this phenomena and see if in fact what is claimed is there.
Scientists worldwide have searched in vain for definitive proof of cold fusion. Positive results have come from about 100 labs, including Los Alamos. Some researchers detect either small amounts of fusion products or releases of heat. Some occasionally report both at the same time, but only a handful can reproduce these effects consistently. In March 1990, believers, the so-called Cold Fusion Club, met in Salt Lake City for the first annual Cold Fusion Conference.
Stanley Pons called the first annual Nuclear Fusion Conference a success.
People aren't so dogmatic. It looks like it's been a success as far as getting the cards on the table.
Pons says he hopes that this conference will fuel productive and open discussion with critics in order to find answers instead of fault with cold nuclear fusion.
But then a series of damaging developments began to unfold. In June 1990, University of Utah President Chase Peterson announced his early retirement after it was revealed that the $500,000 anonymous gift to the NCFI had come from the university's own bank account.
Who think I should resign right now.
That same month, Science magazine raised the possibility of fraud at Texas A&M University, suggesting that researchers there had spiked water with tritium to fake cold fusion reactions. But NCFI Director Fritz Will pointed out that other labs worldwide were also getting positive results.
Is it possible that these 24 laboratories have all spiked the electrolytes? I would think it would be absurd to infer that.
November 1990. In another bizarre twist, Stanley Pons disappeared from Utah, only to surface in France days before he was to meet with Utah's Fusion Advisory Council. The council oversees the state's grant to the NCFI and was in the midst of a scientific and financial review. 2 months later, an independent panel they appointed found evidence of excess heat, but no proof of cold fusion. The council told Pons and Fleischmann to surrender their data for further evaluation.
One has come to realize that Drs. Fleischmann and Pons are not team players.
Frustrated with the chemists' lack of cooperation during the review, in March 1991, Fritz Will resigned from the Institute's Board of Trustees, though he agreed to stay on as director until funding runs out in June. Increasingly at odds with the university, Pons and Fleischmann now face uncertain futures there. Meanwhile, the review of their data continues, and the final verdict on their experiments still remains open. Indeed, some scientists remain convinced that an unusual process is taking place inside the test tube. Few of them think cold fusion will be a practical source of energy. But the worldwide quest to understand this strange phenomenon continues, notably in Japan. There, the government plans to spend $25 million a year on research. Even so, nobody can agree on just what's happening in the test tube.
No, I think you have to invoke a nuclear process, or a set of nuclear processes. Of that I'm quite convinced. I'm as convinced now of that as I was in March. So I think you have a responsibility to say, here are our results, and this is what I think it means. The detailed nature of that, of course, you asked me before, is it fusion? And I said, well, it is a nuclear process, a set of nuclear processes, maybe fusion.
I think it will turn out, after 2 or 3 years more investigation, that this is just spurious and unconnected with anything that you could call nuclear fusion, thermonuclear fusion. I think that, broadly speaking, it's dead, and it'll remain dead for a long, long time.
So what happened? What went wrong? Everybody was worried about the energy crisis and the environment, but why should that have led the University of Utah to announce the discovery by press conference? Few people think it was a case of outright fraud. Instead, it seems likely that a combination of particular pressures led to Pons and Fleischmann's ill-starred announcement in March of 1989. One clue is to be found in events that happened 4 years before the press conference, about 40 miles from Salt Lake City at Brigham Young University. There, a group led by physicist Stephen Jones had also been working on cold fusion for 5 years. Shortly after the March 1989 press conference, Jones circulated an account of the events which led up to it. This is his version. In 1985, one of Jones's group had become interested in a geological puzzle: why the Earth's core is hot. Theory said it should have cooled down by now. Somebody suggested nuclear fusion. Jones and some colleagues discussed the idea. As was the normal practice at Brigham Young, they took the notes of their meeting to the university lawyer. In his lab, Jones prepared a soup of all the chemicals he knew would be inside the Earth. And then he did the same thing that Pons and Fleischmann did. He packed deuterons into metal with an electric current. There's no record of any heat, but they did seem to find neutrons. Few, but enough to note on July 4th, 1986. Jones first heard about Pons and Fleischmann in 1988. He was a referee for a grant application of theirs. He called them and invited them to visit his lab.
And they visited, just the two of them, no lawyers. And they visited with us. We had a very enjoyable chat. We showed them our neutron spectrometer. Indeed, we showed them our data, and in that we showed them the evidence we have for neutrons. We have more evidence since, but we showed them what we had at the time. They were very excited by that. I don't think they understood that it was really a very small amount of neutrons, but we tried to discuss that, but I'm not sure that was completely getting across to them, but they were certainly very excited by the evidence for fusion in the electrolytic cells.
At a meeting between the universities, they eventually agreed to simultaneous publication of their separate results. Pons and Fleischmann had wanted to wait for 18 months. Jones insisted that he was obliged to publish now because his results were ready. They finally agreed to submit papers to Nature on the 24th of March. But on the day before that, without notifying Jones, the press conference was called.
We listened to the press conference with interest. The comment was made, I think, more than once. Boy, we're really glad that we didn't end up working too closely because their nuclear physics obviously wasn't real solid at that stage, and we hadn't realized that they were thinking along these grandiose lines.
Of course, with hindsight, one would prefer not to have had all this brouhaha. One would have preferred a quiet life. But if you have the results which we had in February of this year, and then going into the beginning of March, there's no way you could hide those results. That had to be published. Maybe published, I would have preferred to have backed it up with some further work, but it had to be published.
In February 1989, Pons and Fleischmann were convinced that the phenomenon they'd discovered was fusion on a scale that might be a source of energy. Their conviction fueled great excitement among the University of Utah administration. Pons and Fleischmann wanted more time to continue their work, but the university wanted an announcement to be made. It seems clear that having learned about Jones, they were anxious to beat him to a patent application.
We would do all in our power to have this exploited by ourselves and others for the benefit of cheap energy with little cost to the world's ecology. We would also like it to come to the benefit of the economy of Utah. That's not always easy to guarantee because ideas aren't contained by borders, but perhaps ownership and patents are.
We had written a number of patents by that stage, and the view of the university was that it was correct to announce this via a press conference. It was really the patents which were driving this.
My own feeling is that cold fusion represents more than anything else the American dream. I think cold fusion is the epitome of American dream. I think that Thomas Alva Edison would have been proud to design and invent a gadget such as the gadget that is supposed to make this fantastic source of energy. It has all the symptoms of an American dream. It's the new world. It's a revolution overnight, getting rich overnight, and doing something against the understanding and against the consensus of what our scientific society is. My own feeling is that the American dream turned into an American nightmare.
Scientists and members of the press collaborated in this nightmare. From the outset, media coverage was aggressive, sometimes sensational, often misleading. And some scientists were all too willing to use the media to promote their own ideas. In the aftermath of cold fusion, the propriety of science by press conference has come to be questioned. Physicist Moshe Guy.
I am more disappointed from the role of the scientist in this and not the role of the press. What I'm surprised is about the not very careful way that people, from the scientist's point of view, approach the press. They were a bit too easy about it. I can give you a wonderful example about this. There was somebody made an announcement in the Midwest, and the Washington Post science editor called me concerning other thing, and I said, look, I really don't have time. Let me just go back to my work. And in a funny way, I said to him, but you know something? I heard that there is an announcement from the Midwest. Could you tell me what has he done? How has he treated his electorate? Do you know anything? And the Washington Press science editor rolled in laughter and told me, that result? Oh, I wouldn't put it in my paper. No. And to a certain extent, you have over here a very funny situation. You have a non-scientific publication which had an impromptu set referee system. I mean, this editor probably doesn't know if it's right or wrong. What he did is probably call some scientists, and they gave him a list of things which were wrong. And that impromptu referee system, which is also incorrect, you have to have the paper in front of you before you can comment on it, have given the editor some comments, and that editor came to the conclusion that he will not publish it. So in a sense, let's just amplify this example as an example of the fact that the press was not the one which was irresponsible. It was the scientist who was irresponsible. I think the scientist should have not gone to the press on March 23rd and thereafter. It should have been done in the way science has been done. Science has to do its thing, and its thing is working in publication, going to international meeting, have a scientific discussion, checking, rechecking, double-checking, verifying everything, and once it's true, then you can go to the press if it has any interest to the press.
The months stretching to years of legal and commercial pressures must also have had an effect on the smooth running of the scientific process.
My own belief is that Pons and Fleischmann, for a very particular reason, had come to nurture a delusion about what was happening. Remember that they had been working on this project for 5 years before they had their press conference. They'd been convinced at an early stage that they were observing fusion, and much of their later work was an attempt to confirm this by measuring neutrons and gamma rays. And they were convinced that this discovery was going to be of immense importance, as indeed it would have been if it were true, and was going to make a great fortune for somebody, themselves included. And so they kept it very secret. As a consequence, they were entirely isolated from the natural day-to-day skepticism of the scientific community, and they didn't get the help from the scientific community that they would have gotten. So, in my opinion, they were able to nurture this delusion that they were measuring fusion only because of the secrecy that they had themselves imposed on their work.
Because of the intense public interest in this, and what is obvious also, I guess in the States, the commercial interest in this as well, the patent lawyers are in all the time on this, that this exchange of information has not taken place. And so what you're left with is almost like a religious dispute You have a group of people who believe very strongly that cold fusion exists, and then another group of people who believe very strongly that it doesn't exist, simply because the two have not been able to talk to one another in a way which would allow them to resolve the similarities and differences between their experiments.
I would say it's been bad all in all. The only good thing I think that came out of it is if the public will understand that if we want to save our planet, if we want to get a solution to our energy problem, those solutions will not come overnight. Science is not something that occurs overnight. It's very hard to do an experiment, a good experiment. I think the public should realize that science is not something that is done in a hurry. Science has to be allowed to do its thing, and it takes time to do good science.
I did see a bumper sticker that said, "Be merciful to electrochemists, as they know not what they do."
A few days ago, I got to thinking, gee, it's a shame Richard Feynman isn't alive to see all this cold fusion stuff. He would have gotten a big kick out of it. Assuming that cold fusion goes the way of polywater and N-rays, who gets the jars?
All of us in the industrialized world are already using too much energy. Think about it. Couldn't you live with a smaller house, with one or no car per family, with just one product of detergent, with half of your plastic equipment? Don't tell me you can't.
If I throw a match into a box of gunpowder, I get more energy out than I put in, too. Could this mean something?
I guess it is time to close down this forum. Any objections?
Funding for NOVA is provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. Major funding for NOVA is provided by the financial support of viewers like you. For a transcript of this program, send $5 to this address or call 212-227-READ.
This is PBS.
Most NOVA programs are available on videocassette. Schools, businesses, and organizations interested in purchasing videocassettes should call 1-800-441-NOVA.